Someone took one of the most advanced 3D rendering techniques used in AI research, the kind that normally needs a dedicated GPU viewer and a beefy graphics card, and made it run inside a terminal. Just a terminal. No GPU required, because the output actually looks recognizable. That technique is called 3D Gaussian Splatting. If you haven't heard of it, here's the short version. You take a bunch of photos of a real-world object or scene, and a neural network learns to represent that scene as millions of tiny 3D blobs, called Gaussians, each with a position, a shape, a color, and an opacity. When you render them all together, you get a photorealistic 3D scene you can move through in real time. It came out of a 2023 research paper and it immediately blew up because it was dramatically faster than the previous standard, NeRF. Big companies, game studios, and research labs are all over it. And now a developer named Darshan Makwana put it in your terminal. The project is called tsplat. You point it at a pre-trained Gaussian Splat file, the standard .ply format, and it renders the scene directly in your terminal window using colored ASCII characters and Unicode blocks. It works by projecting the 3D Gaussians onto a 2D character grid, sorting them by depth, and blending their colors the same way a real renderer would, just at the resolution of your font size instead of pixels. The result is a lo-fi but spatially coherent view of the original 3D scene. You can actually navigate it. There are keyboard controls to rotate and move through the scene. It runs on CPU only, written in Python with NumPy doing the heavy lifting. On a typical scene with a few 100,000 Gaussians, you're getting real-time or near real-time frame rates, depending on your terminal size and hardware. What surprised me was how immediately recognizable the scenes are. The character-based rendering isn't just noise. You can clearly make out structure, depth, and color. If someone rendered a room interior, you see the room. If it's an object scan, you see the object. The brain fills in the rest. Now let's be honest about what this doesn't do. This is not a replacement for any real Gaussian Splat viewer. The visual quality is nowhere near what you'd get from tools like SuperSplat, the official InRE viewer, or any WebGL-based renderer. You're losing most of the detail that makes Gaussian splatting impressive in the first place. Complex scenes with fine geometry, hair, thin structures, text become unreadable at terminal resolution. The frame rate also drops hard once you go above a few 100,000 Gaussians, which is small by professional standards. Most production splat files have millions. There's also no support for loading the newer compressed splat formats, or the extensions that have been added to the ecosystem since the original paper. You're working with base .li files, which limits which pre-trained scenes you can actually use, and the navigation, while functional, is basic. You're not going to do a smooth cinematic walkthrough of an architectural scan in your terminal. But here's the thing. There are real use cases where this matters. Imagine you're running a pipeline on a remote server. You've trained a new splat model, and you want a quick sanity check before pulling gigabytes of data to your local machine for visualization. With tsplat, you SSH in, run the viewer, and in 5 seconds, you know if the reconstruction looks sane or completely broken. That's genuinely useful. It also works as a teaching tool. Gaussian splatting is mathematically dense. Watching the alpha compositing and depth sorting happen in a medium you can literally count the characters of makes the algorithm more tangible. The code is clean and readable. It's a legitimate way to understand what's actually happening under the hood. For CI pipelines, you could imagine tsplat becoming a lightweight regression check. Does the scene render without crashing? Does it hit a minimum quality threshold? Is the geometry roughly in the right place? Automated quality gates for 3D reconstruction pipelines running on headless servers. So why does this exist at all? Because the standard tools for working with Gaussian splats assume you have a GPU and a display. That's a reasonable assumption for a creative professional or a researcher at a university. It is not a reasonable assumption for a server process, a containerized deployment pipeline, or someone working in an environment where installing a graphics stack isn't possible or allowed. The entire history of terminal tools is developers solving exactly this problem, taking something that assumed a rich graphical environment and making it work in the most constrained possible context. tsplat is that for one of the most modern rendering techniques that exists right now. It's not trying to replace anything. It's filling a gap that genuinely exists. And the fact that it works at all, that you can take a 3D neural radiance structure and project it into a grid of ASCII characters and have it look like something, is kind of remarkable on its own. If you work with 3D reconstruction or you're learning about Gaussian splatting, this is worth 5 minutes of your time. The install is a pip install and a single command. Link to the GitHub is in the description. Next episode, we're looking at a tool that runs a full object detection pipeline on a Raspberry Pi with no cloud dependency whatsoever. Sub 100 megas inference, fully offline. If that sounds impossible, stick around.